All right, I'm going to talk through some ideas that the chapter has on threads. Half the chapter is very good for us. It's the right level, the right nuance, and other parts of the chapter, when they get into how to use the API and the code, we aren't a class yet, maybe for better or worse, where we're getting into actually calling. It's just important to realize that we understand what threads are. Let me get out of presentation mode because I'm going to want to use the system here. So yeah, I'm going to skip over. Tell them where you're headed. But the idea of a thread, and I was discussing with a student last time. Think of I was likening maybe an operating system as something like a chef in a restaurant, and you don't deal directly with the cooks or what's going on back in the kitchen. You might send a message via a waiter, and that brings it. And think of the managing chef as the operating system, and processes are maybe the different cooks. When a cook gets started, they may start a pan heating. They might be chopping an onion, and at the same time, told the sous chef or something to prepare something else. And those are threads, a way to think of it, the different things that a cook is doing at the same time in response to trying to complete a process. So these things that are running whenever you run any program, it's divided into threads. And if you get the idea that dividing up a task can make it work faster, if the operating system can juggle them, then threads pretty well at the level that we need it. If you want to see some threads in action on a Windows PC or in your Windows Server VM if you're on a Mac, and there's ways to look at this in Macs, if you go to the Performance tab and open up the Resource Monitor and get on the CPU tab, you can see a lot, including how many threads every process that's going has open. So you can kind of think of a thread a little like a subprocess, and something that's running on in parallel. And the chapter also talks about multi-core types of programming. And so this computer has 8 cores, really kind of 4 CPUs, each have 2 cores. And so each CPU is working a little different. And so you have kind of these hardware threads, if you will, where it can divide it out and use a different CPU, this multi-programming. But even on one CPU, it can, since it's multitasking, it can divide the task up. And that's pretty much the threads idea. Some true things. Threads are run within an application. You can write a program, start and kind of go do this task. And some of the things that a thread might do is, okay, you go update the display, and I might be still calculating something or fetch data or spell checking, specialized things. Think about how you might divide up a task, but things that could run in parallel a little bit. And the idea is that a thread within a process is lightweight. Remember, for the operating system to start a process, it has to do a lot of validation of what memory can that process that I'm starting allocate? Does the person starting the process have the authority to do this, etc.? Once they're sort of in that box, if you will, think of it as a subset of the whole CPU and operating system, then the threads are lightweight. It's like, okay, you can do what you want within this playground. You cook preparing this plate can do what you want at your station, without anything checking in. Sometimes it can simplify code. This idea, it comes with object-oriented of kind of breaking a task. Okay, I'm sending out to the display, or I'm spell checking, and so rather than having the code all together, and it's hard to separate what the code is doing because it's doing the multitasking itself, it just says start this little sub-process, chop onions, rather than maybe chopping onions while I'm melting my butter and that kind of thing. And everything, including kernels, are typically multi-threaded. It's the way things go. You might think in a classic client-server model, we've been working a lot with web pages. It's not so much that the websites and the configuration is that important overall. I use the Apache and the IIS a lot in this class because they're examples of getting underneath and configuring the operating system right. We don't have too many ways. Same thing with SQL. It's practice installing, but it's also practice at configuring and looking at an error log. But both then web server and a database server have this thing. A request comes in, then okay, go take care of this. And then I'm going to go back to listening and waiting for another request. Okay, so it's a way for the server. When I say server here, I'm talking about like a database server or a file server or a web server that's operating, on maybe a hardware server, to just make better use of its time and dispatch this off. Now it's the operating system that's managing this, and that's part of the magic, and you get lots of benefits if it's programmed right. The user gets a little bit more responsiveness. The server can get back to, like a web server, back to what it's doing more cheaply. You can scale better. That is, if you get multiple cooks involved, you can serve more people at a time. A lot of this is if you just think about, well, I'm getting more things being worked on at a time. You've got to realize that as more things get worked on, the OS is dividing its capability or the hardware among more things, so it can reach to a point where it gets over loaded and it really starts thrashing rather than gaining all these benefits. The idea is make the best use we can of the hardware resources. I gave the picture there of this multi-core programming, and that's got a little bit more, there's this comment it puts pressure on. With multi-cores, it's a little harder, and you have to be a little closer to the hardware to write some of the code. And how do you balance where's a good place to divide the activity? Should I really, is chopping onions by itself? How about chopping onions and celery at the same time? How do I test? And if things are dependent, I need to complete this before I've completed that. It's just work and some programming overhead, but getting it done lets things go a little bit better. I'm going to bring up this and looking at these multi-cores. It seems to be dividing the work pretty well. What work there is, well, about 48% CPU usage. And maybe it's this recorder and everything. It's coming down now, so that's busier than I thought it would be. I'm going to crank up a VM and just see, sometimes you can pick out. So that VM, when I defined it, I said, maybe give it 1 core or 2 cores or something like that. This still seems pretty well divided, but it's a little bit like that first and second. Now they're all kind of off the top. So I didn't get the example quite that I wanted. But 0 and 1 weren't as loaded as maybe 6 and 7. So VMware, just by inspection, I can't prove it, said, okay, I'm going to really use multi-core out to them for a while. It's subsided there. Now as this thing waits. But the point is that VMware is a very complex, and very close to the hardware activity that you can kind of see that now it's kind of worked down, and it looks like 4 and 5 are carrying the lion's share, as VMware says, okay, you can have these cores back, but I might keep these 2 as long as I can until the operating system maybe says you can have them back. So not a great deal of drama, but that's the idea, that parallelism, we're actually running 2 computers at one time, right? A Windows server and that, and concurrency is more than one task is making progress. They're concurrent. Sometimes you worry about concurrency is race conditions getting to a resource. But we're here with what are the good things that happen. So we saw some task parallelism in that picture, distributing the work across cores, and it needed, if it was 2 cores and participated in running that VM, say, they needed to be able to access that same data, that virtual hard drive, and so forth. So that's the good thing about threading, and the operating system, at least from our viewpoint here, handles it. We just need to realize what they are. So there's cores as well as within a core hardware threads, and they have some examples that we have a multi-core, and I bet you yours is a multi-core computer as well. So if you kind of needed a picture, rather than this, then this, then this, well, it can be doing more things at one time by dividing up the work and managing it across the cores. Okay, and so yet in another picture, the idea that, and it does have to duplicate some of these data, the registers, but in a multi-threaded process, you can kind of think the cook's chopping onions, the sous chef is, sous chef kind of takes care of like salads and lettuce and like that, and they're sending somebody back to go get a fresh steak for the cook to cook later, and those are threads that then need to be organized and brought back together. So you don't need to know Amdahl's law. You might have had a question, I don't know. But the idea is, there are performance gains. It's not going to be linear. Okay, I was kind of alluding to that, meaning, gee, if I have 2 threads, it'll work twice as fast. If I have 5 threads, it'll be 5 times as fast. The overhead starts coming in. They're a little bit like, and this is almost like communications on a project. As you add people to a project, the number of necessary intercommunication channels goes up somewhat as the square of the number of people on the project. And so, after a while, it's a project size can be unwieldy, and there are some numbers, but after a while, it's not going to get any faster. It's going to start spending more time organizing itself and scheduling itself than it is going to do anything else. So I'm going to kind of click through these. This is just getting down. It's not that useful. We're not going to be writing threads, but every system has threads. They had, here's some specific libraries and how they or what the library names are available. Right. And you can kind of then say, well, there's, threading example is, it's kind of a many out of a one process. And that's been the example that I've been using. That is, I've got this process and I start these multiple threads, and that's the many to one kind of thing. It does have some issues that if that cook doesn't get those onions chopped, then it's not going to be able to saute the steak and butter they're getting, and so there is that blocking, and a couple of things. And this, that's a model. There's you can divide and have a process. It's kind of got one thread in the kernel that's managing one thread out there in the user system, and you can have more things going on in that model. A little more overhead involved than though in the operating system, as it's got more processes and more time spent managing the individual threads. And the idea is, well, you can have a kernel thread that says, okay, I want then many. So I've got several kernel processes that are paying attention to many different subprocesses at the same time. And if I'm doing sort of a few file things, and I might need to wait for 3 or 4 other things to collect together. I don't know, it's almost like if you think about how web pages are sent in packets, right? There's many servers to get involved, and the server has to then wait for all the packets to coalesce before it can really render that page, and that's a many-to-many version of kernels. Okay? I wouldn't even bother about the two-level model. It's about like that M to M, and just many things going on in the kernel that map to many things going on sort of on the application side. And here's the part you don't need to know about which libraries and how to code them. It's not bad stuff. It's actually kind of fun to dive that deep. That's not our that's not our goal in this course or our mandate. And thank goodness in some ways, but we would have had a very different start to the course if we did. And so this is C, or it would look a little bit like maybe C++. I went back and have been watching some Silicon Valley. No, not Silicon Valley. This was the interns. Anyway, Owen Wilson and Vince Vaughn, they go on as interns at Google. You might have seen it. Just have HBO Now was flipping through. And they were talking about, I see you did C++. They put it on the thing. And you say, well, yeah, I got a C+ in programming, and I think it was basic program, but so it was really down, but anyway. So the Owen Wilson character was confused or didn't really realize C++ was this, and he gave himself an extra plus because he got a C+ in the programming. But anyway, the point is Java, C, maybe C++, perhaps assembler. Those are the levels at which a lot of this close to the operating system interaction take place. We just take advantage of it. Okay. There are times when threads will be done. It's almost like on our behalf. Okay, the system will see, or it will just automatically create the threads or pull them from a pool. Turns out if you dive underneath how IIS works and managing multiple sites, that's really how it goes. There's a pool of threads, and we just give it to the next request that comes in, and as long as you have enough, or if it needs to create more. But that was happening or will happen on an IIS site, and you don't write the code to say, start a new thread. It kind of does that for you. All right. So I kind of said, think about threads. The messengers, or these are Cook's assistants waiting for something to happen, it gives maybe an upper limit to how many threads will be going on, but it's just a way for the operating system to manage the resources rather than sort of waiting, or you just tag a new one rather than even kick off a start. So it kind of separates the task to be performed from the mechanics of creating the task. So the analogy back in the kitchen would, golly, just maybe the cook gets to holler onions, and somebody that's just been standing by that can do a lot of things jumps to and starts on that thread, rather than the cook saying, okay, Danielle, I want you to chop me some onions now. And here's some examples for, golly, is Fortran still out there? That was my first real language, but code examples that we really don't need to worry about. Same thing here. It's kind of how Apple would manage that idea, but a little beyond our need now. Okay. There are issues, and you can just imagine that there's the semantics, the wording. How do you, if you're going to fork into multiple threads or execute another one, getting the parameters right. That's what that first one is about. How do we handle the signals? I've got sort of the onions and go for the steak, but what if they needed to interact two threads? Maybe there's one knife, okay, to chop, and I've had somebody chopping onions and somebody chopping celery. I mean, there's a mundane sorts of examples, but the operating system needs to handle that. Are they synchronous? That is, I've got to, get them done at the same time, or is it a little asynchronous and one can sort of happen? That's why a lot of times chop your onions and garlic ahead of time, and then it's asynchronous, and you have a little bit of an inventory and canceling a thread if you either don't need it anymore or it's been superseded. Those are issues, and the book goes into a little bit more detail. If you sort of understand, yes, it's hard to manage multiple things going on at a time, then you probably have what we need for this class and our level. Okay, and these are a little more detailed than we need to the questions here, and there are ways that when you get at that level, you can manage it. All right, and Unix, which Linux is built on, is kind of uses signals. We talked roughly about how those went, but it's a way to kind of, gee, I'm in one thread, I need to signal another thread. Are you done yet? Are you finished with the knife? And those kinds of things. And so it's just the way the operating system helps inter-thread communication. Okay, and you can define handlers. Don't think you get into that in 1301 at all, but even in object-oriented programming, there's more, the idea of having sort of a waiting, or you start a process that's waiting for a signal, and then it kicks off. Downloads work that way a little. Gives you a sense of that. You click on something, download, the browser comes back, and the download then indicates it's done. It used to be that was more synchronous. You kind of dead in the water. Back when the web was basically all you did was download files. You just waited for that download, and then you could click on another file. It looked like a large directory. But if you're going to break it into threads, there needs to be ways for those threads to call each other. And is this signal for me? Is it for someone else? So kind of and that's why threads and processes get IDs and that. So when a thread starts, if you're managing it, you need to know its ID, and that's how you contact it. And there's the idea that maybe we don't need a thread, so there's a little bit more work if the system's waiting for a thread to complete, and you say, well, I really don't need those onions. The customer said, I don't want onions on that steak, so back it comes. And so how do I get word out to that person who's chopping onions? I really don't need it anymore, and it can be handled in software. This one just raises, well, gosh, that's another issue for the operating system to cancel. So one way is the cook can keep looking over to see and ask, do you still need these? Do you still need these? The other one just says, hey, quit chopping the onions. Enough with the images or the similes and metaphors. And this is getting down into the weeds a little bit for our use about what happens while this is getting canceled. All we can really see from our situation is that finally these things terminate. You can over here I think it's maybe here, see some of the sub-processes, and you can work on and end a task, or you can end a whole task tree, and it's just realizing that if one of my things gets canceled, how do I know as the main processor, the one that's waiting for it, that I am done now too? So that needs to be signaled, yes. And Each thread, little program needs its own. Each cook needs its own workspace. Okay, so it's maybe I need a copy of the the menu we're working from or the recipe that I'm going for, and so that's an analogy is this thread local storage, something that I can look at that lets me do it rather than shared. At restaurants, fast food, a lot of times they have the big marquee right up, and they're looking at, and it's always somebody else's order rather than mine, but. And so it's right, yeah. In a thread pool, it's nice to know that they'll have their data set, and it's similar. I don't know if you did much in 1301 programming with the idea of static variable static data that's not dynamic, kind of sometimes can't be changed after it's created, and but again, that's getting down to mechanics that are a little bit more detailed than we need to get to. So, as is some of this level, right? And these are just inventions, little maybe tricks of the trade the operating system uses. Is sometimes is this a big real process going to the fridge for another, some more cream or something. A recipe isn't quite the same thing as, pounding out a fillet to make a schnitzel or something like that. So the idea is the idea of a lightweight process that manages a thread. Think of it as, it's not quite as involved because the process isn't as involved, and that's just a scheduling trick. And then they have, we've seen it in Windows, at least in that picture, but Windows manages threads, kind of with a thread ID, and you could, with C assembler, look at some of the details, but think of the PID, the process ID, as the main thing, and it kind of as a process as it escapes out of the kernel into the user space, but it's these pointers are the in C or C#, you deal everything with pointers or places in memory where it's going to keep track of all this, and then it starts a thread. They're tasks rather than threads, and you can list all classes or list all tasks in Linux, a lot like we're looking at this thing here. And so clone says, well, we've got the same addresses, so we can share information. Getting into the details, but a struct, that's kind of static data. And if we're kind of sharing something that's fixed there outside of our control, but we can read it, that's a good example of static data. So I kind of started, I think, with showing some representation, and at the level we went, I felt like the last few were sort of blah, 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 until and if, and that this isn't the course, we get down to the C level. It is really hard to see the idea of threads and manage them and experience some of the pain, but realize that you know how to check for them, at least broadly, and you realize that the CPU is going to manage and keep the scheduling, and I think you can envision it, and that's the important part for us.